So revisiting section 9.1, and we're going to prove how to differentiate this thing here, because we didn't have a justification for the derivative they tell us in the book. So now that we've seen the chain rule, we can do this. U is k times x, y is sine of u. du by dx, well, the derivative of k times x is k. dy by du is cos of u, and then dy by dx equals dy by du, which is cos of u, times du by dx, which is k, and that is k times cos kx. So there's that result. Now, in fact, let's think a bit more carefully about that. If I have x, instead of x, if I have a k of x, so I've got a function is k times x. So if y equals f of k times x, in fact, we can do even better than that. Y equals f of kx plus 1, kx plus, I don't know, a. So this is a linear term. So instead of an x, I've got a linear term. Well, let's let u equal that linear term. Y is f of u. dy by du equals f dashed of u. du by dx is kx plus a. So by the chain rule, we have dy by dx equals k, oh sorry, the derivative of kx plus a isn't kx plus a, the derivative of kx plus a is, of course, just k. So dy by dx is k times f dashed of u, and u is kx plus a. Okay, so in other words, if you have a function of a linear term, a linear expression rather, if you want to differentiate that function, the function is the same as the derivative would be, but then just times by the coefficient of the x in the front. Okay, so that is where those results come from. And now we can say, okay, well, if e to the x, if I differentiate that, I get e to the x. So if I got e to the k times x, well, that is e to the x differentiates to the e to the x. So e to the kx differentiates to e to the kx, but I've got to stick a constant in front of it. So if that's y, dy by dx equals that. And it's just this result here. If instead of an x, you've got a linear expression in x, then differentiate and have a linear expression in x. But don't forget to times by the coefficient of the x. And obviously then the same thing works for the derivative of cos. Having a look at y equals natural log of x, well, in this case, that would be the same as e to the y equals x. So if we do, if we find dx by dy, then we get e to the y, because the derivative of e to the y is e to the y with respect to y. And then we can use our chain rule, special result of the chain rule, that 1 over dx by dy is dy by dx. So dy by dx is 1 over e to the y. Okay? But e to the y, it says here, is just the same as x. So dy by dx is 1 over x, and there is that result. Okay, so those are all the results from section 9.1 and 9.2. Only we can show where they come from sort of properly. Now let's have a quick look at what we do with those. So here we're just differentiating as we know we can. Sine 2x following the rule, cos 5x following the rule. Here I can differentiate the first bit, differentiate the second bit, and add the results together, and the same as we did with polynomials. We then just have to worry about what can we do with derivatives. Well, we can find stationary points. Now this is where you really need to know last year's differentiation well. So how do you find stationary points? Well, stationary points are defined by the points on the curve where the first derivative equals 0. So find the first derivative, put it equal to 0, and then solve. Now when you've got to solve it here, we've got a bit more of a problem because we've got an equation involving a sine, so we've got to solve a trig equation. But that's fine, that's not a differentiation problem. If you're stuck on that, you need to go and look at the trigonometry chapters. Okay, so the equation that you've got to solve now could involve sines and coses, and of course in a second could involve e to the x and natural log of x. But having to solve an equation with those things is not a differentiation problem anymore. you need to sort of refer to those chapters, make sure you got those techniques going well, okay? So where are we? We can differentiate e to the x, natural log of x, sine x, cos x, all of those things where you have a linear expression in x instead of just having an x input. There's one more thing that we haven't looked at, and that is this. What if we've got y? What if we've got y equals a to the power of x? So something to the power of x. Now this one, we sort of don't tend to use it all that much, weirdly, in A-level questions, but this is one of our sort of functions that we know about, is it? It's an exponential function, so we need to be able to differentiate it. And the trick is to do it like this. We're going to think about this thing here, e to the natural log of ax. Okay? Well, e and natural log are inverses of each other, aren't they? So this is like saying take ax and add 5 and take away 5. E to the natural log of ax is an e and a natural log, so that would just be ax. So this is just a weird way of writing ax. So y equals ax, y equals e to the natural log of ax, and that is the same as e to the x natural log a by the power rule on the logs. So now I can differentiate, because natural log a, sorry, that is e to the x log a times by the derivative, which is natural log of a, times by the derivative of this thing here, right? But so this is the chain rule. This is the quick version of the chain rule. So if you like, that's the thing in brackets. Differentiate with respect to the brackets times by the derivative of the thing in the brackets, so times by natural log a. And then e to the x natural log a is, well, e to the x natural log of a is that. So that is natural log of a to the x. Okay, so there's our derivative of the a to the x function. Now if you think about all the functions that we know e to the x, natural log x, we know a to the power of x, we know cos and sine and tan, and then we know polynomial functions, right? Something to the power of something. Well, we don't have a derivative of tan yet, but we'll be able to get there soon. We also know sec, cosec and cot. We haven't got derivatives of those, but we'll have those by the end of the chapter. So by the end of this chapter, we'll be able to differentiate all of the functions that we have met so far and combinations of them. Just quickly, example 5, we can differentiate these two things separately using the standard results. This one here is a chain rule, or if you like, you can bring the 3 down to the front and have it as 3 log of x and differentiate from there. This one here we can need to split up into 2 separate fractions, so 2 over 4e to the 3x and minus 3e to the 7x over e to the 3x, and then use the power rules to simplify to this point here, and we can work from there. Okay, so that is section 9.1, 9.2 and 9.3. A lot of information so far, but there we go. Good luck.